So when we talk about the quotient rule, let's, start with a quotient here. So let's consider f of x equals x to the 6th over x to the 2. Okay. We know x to the 6th divided by x to the 2 is the same thing as what when we simplify it? X to the what? 4. Okay. So then, f prime of x would be what? What would the derivative be? 4x cubed, yeah, right? We can just take the derivative of that. Okay. Since, x to the 6th over x squared is the same thing as x to the 4th, except when x is 0. Okay, except when x is 0, these two things aren't equal, right? Because 0, this would be indeterminate form, and this would be then a value of 0. So, but anyway, the derivative is 4x cubed. Okay, easy, right? But let's, again, kind of do what we did yesterday. Let's reconsider. Okay, f of x equals x to the 6th over x squared. Okay. And then let's take the derivative of x to the 6th and x squared individually. And divide the results. Okay. So the derivative, for example, right, of x to the 6th, the derivative with respect to x of x to the 6th, so that would be 6x to the 5th. And the derivative with respect to x of x squared is going to be 2x to the 1, or just 2x there. So those are the individual derivatives, right? So we just took the individual derivative of the numerator over the individual derivative of the denominator. Actually, we'll put it over top of them now. So there we'll put them on top. So 2x, and not denominator, and 6x to the 5th in the numerator. And so now we divide. We can simplify, right? So 6 divided by 2, that's going to be 3. X to the 5th divided by x is x to the 4th. So, with those results, is it true, in general, that the derivative with respect to x of f of x over g of x equals f prime of x over g prime of x? Based on these results from 1 and 2, is it true in general that the derivative of f divided by g is the same thing as just saying f prime over g prime? Do we get the same results? No. No. Okay, it is not so. Again, if it's addition, so if it's f of x plus g of x, then yes, the derivative of f of x plus g of x is equal to just f prime plus g prime, right? F plus g, the derivative of that is just f prime plus g prime. If it's subtraction, yes, it's still true. F minus g, the derivative of that is still f prime minus g prime. But when it comes to a product, when you're multiplying two functions together, when it comes to a quotient, when you're dividing two functions, right? The derivative of a product is not the same thing as the product of the two derivatives. And the derivative of a quotient is not the same thing as the derivative of the quotient of the individual derivatives. It's not the same thing, okay? So watch out with products, watch out with quotients. Yes for addition, yes for subtraction, but not for addition, or not for product, and not for multiplication and division. So what is is there a relationship here? And the answer is yes. There is a way to simplify a quotient, or to do a quotient without actually, doing that. So the quotient rule for a derivative. Okay, the derivative, excuse me, with respect to x, okay, of a quotient. So we'll just do a generic kind of f of x over g of x thing. Okay. Is equal to g of x times f of x, sorry, f prime of x. Okay. G of x, the denominator, times the derivative of the numerator, f of x. So g of x times f prime of x minus f of x times g prime of x. And so you're like, oh, okay, this is kind of like the product rule, right? Kind of like the product rule. All over the bottom squared. Okay. Ugh. What a mess. But that's it. Okay, that's it. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay. And this is something, should you take calculus, that you'll memorize. And it's really not that bad. Okay. It looks yucky, but it's really not that bad. Okay. In fact, there's a little rhyme you can use. I didn't use this rhyme when I was in calculus, but you can if you want. Okay. I'm going to just call this low, and yeah, all right, whatever. And we'll call this high. Okay, it's like low D. So the little rhyme you can say is low D high minus high D low over the square of what's below. Sounds like something like, I don't know, a leprechaun would say or something like that. Low D high minus high D low over the square of what's below. Okay, maybe Mr. Goff, if you guys have him, you can have him like do a little jig or something like that. He's got that red hair. He's Irish, right? So, okay, so that's a little way to remember it. Low times D high. Low D high. So low times bottom times the derivative of the top minus high, the top, times the derivative of the bottom, D low, over the square of what's below. Right? So that's a little rough, if you want to remember it that way. Okay. However you do it, doesn't matter. Okay. So let's see this in action. Right? Let's see this in action. So let's go back and let's just check it here with x to the 6 over x squared. Right? We already know that it works. No, we already know we don't need to use the quotient rule here. Right? We don't need to use the quotient rule here. We can simplify that. And in fact, that's what you should do. Right? Like in a problem like this, you should not use the quotient rule on this thing. You should try and simplify it first if you can, and then take the derivative of your answer, okay, of the simplified version, because it's much easier this way. But let's just make things hard on ourselves, okay, and let's find the derivative of x to the 6th over x squared using the quotient rule, okay. So in terms of the quotient rule, right, the x to the 6th will be like f, the x squared will be like the g, okay. And so then to kind of fill in our blanks here, the derivative of f over g is going to be g, so the x squared, times f prime. So the derivative of f will be 6x to the 5th minus f, which is the top function there, x to the 6th, times the derivative of the bottom, so the derivative of x squared is 2x, all over g squared, so the x squared squared. One of the things that calculus will develop in you if you, again, decide to take it, should you move on to something, one thing that doing calculus will develop within you is like meticulousness, attention to detail, because when you miss a negative, or when you flip-flop the, if you do like G prime times F here and F prime times C there, if you mix those up, it's going to throw everything off, right? So you will develop a more meticulous nature should you take calculus, just out of necessity, right? Because you want to get these things be accurate and all that. There's, little idiosyncrasies and stuff like that. So anyway, we simplify here, okay? So x squared times 6x to the 5th, 6x to the 7th, okay? 2x times x, 2x to the 7th, all over x to the 4th, right? X squared squared. One of the beautiful things about calculus too, not maybe that meticulous stuff isn't very interesting, but calculus really is the culmination of all the things that you learned like so far. You're going to have geometry in calculus. You're going to have all your algebra, algebra 2, pre-cal, all that stuff. It's all going to be in calculus. It kind of brings everything together, which is kind of nice, in one way or another. All right, but lots of algebra simplification too. So you'll get better. You'll get good at that too, the more you do it. 6x to the 7 minus 2x to the 7th is 5x to the 7, and then over x to the 4th, and so then the x's can cancel, and we're left with 5. Whoops, I made a mistake here. 6 minus 2 is 4, Mr. Whitmire. There we go. Speaking of meticulous attention to detail there. Okay. 4x cubed. That's what we end up with. Okay, which is exactly what we got from up top there, right? 4x cubed, 4x cubed. Okay. Questions on any of that so far? We'll do like another 1 or 2 examples here. Maybe 3. Okay, 1, 2, or 3 more examples. Well, 2 or 3 more examples maybe. Here's what I'll say now. Alright. Let's try another one. Okay, we'll just say find the derivative of each. Okay. All right, first one here. Let's do 5x minus 2 over x squared plus 1. This is a bit diving in head first here, but that's okay. So again, we have a quotient, right? And this one we really can't simplify, not like we do with the x to the 6 over x squared. Really, in this case, we do want to use that quotient rule. We could break up the numerator. We could make it, 5x over x squared plus 1 minus 2 over x squared plus 1. But then we will have taken one quotient rule and made it 2 quotient rules. And I don't think we want to do that. So we'll probably just leave it the way it is here. Okay, so again, there's our 2 functions. And so then f prime of x will be low x squared plus 1 times the derivative of the top. What will the derivative of the top be? What's the derivative of the top here? So the derivative of 5x is just 5, and the derivative of 2 is 0. So we're left with just a 5 there. So there's the bottom times the derivative of the top minus the top, okay, 5x minus 2. And what's the derivative of the bottom? What's the derivative of x squared plus 1? Just 2x, yeah, just 2x. Again, the 1, the derivative of 1 is 0, so it's gone. All over the bottom squared. Okay. Now, on the AP Calculus test, all right, if you're in a free response question, which is like, the free response is kind of like the essays of calculus, where you kind of just, you just answer the question, and it's like you show all your work and stuff like that. And a free response question, if they ask you to take the derivative of something like this, you do not need to simplify it. You may stop right here and say, done, I'm taking the derivative. You don't need to simplify, all right? And that's just one of the perks of the free response questions. However, if this were like a multiple choice question and you were being asked to take the derivative of this, then most likely you would need to be able to simplify this, because you got to be able to match your answer to what's on the multiple choice. And most of the time they do simplify their multiple choice answers. So let's just simplify this here. It's not terrible. We get 5x squared plus 5 when we distribute the 5 there. And let's see, it's going to be minus 10x squared, but plus 4x. Okay. We're distributing kind of two things simultaneously here. Both the 2x gets distributed, but then there's a minus in front of that parentheses. So it's 10x squared, but minus 10x squared. Then minus 4x, but then minus and negative 4x becomes plus 4x there. And then I'm going to actually not just leave the x squared plus 1, unmultiplied there. I think that's better because it's a kind of factor there. It's nice. Again, it's a matter of sometimes it's not so clear about what to do, but anyway. 5x squared minus 10x squared is negative 5x squared. 5 plus, the plus 4x then plus 5. Okay, and I'd say that's probably the most simplified it can be. Some of you might argue we should square out the bottom, and yeah, that's something we might need to do. I don't know. Debatable about whether that's more simple or not. Okay, but there's maybe the most simplified answer. Okay. So the calculus was just that very first step, and that's algebra. Right? That's algebra. Questions on number 1? Does that make sense? Anything unclear about what we did there? All good? Okay. Let's try another one here. And it's frozen. There it goes. X squared minus 3x plus 7 all over the square root of x. X squared minus 3x plus 7 all over the square root of x. Okay, we're going to take the derivative of this. I can't do this without, it's going to, anyway, all right. Do we need to use the quotient rule here? Do we need to? Could we use the quotient rule? Yes, absolutely. It's a quotient. But do we need to use the quotient rule here? A numerator can be broken up over the denominator, right? Earlier here with number 1, I said we could rewrite this thing as 5x over x squared plus 1 minus the 2 over the x squared plus 1. I could break up into 2 fractions there if I wanted to, right? What I meant was like... Right? But that wasn't helpful. We went from 1 quotient rule to 2 quotient rules. But here, with this particular denominator, if I rewrite square root of x as x to the 1/2, if I break up the numerator over this denominator, we can actually simplify this down and avoid having to do a quotient rule altogether. Right? X squared over x to the 1/2, well, they have the same base, we just subtract the exponents, and so it becomes x to the 3/2. Right? 3x divided by x to the 1/2, again, that's x to the 1, so again, same base, subtract the exponents, we have 3x to the 1/2, and then 7 over x to the 1/2, we can rewrite that as 7x to the, well, there's no x up there, so it's just 7x to the negative 1/2. And so we can avoid the quotient rule altogether here, because we can break that numerator up over the denominator and actually simplify it. And so when it comes to taking the derivative, we're going to end up with 3 halves x to the 1/2 minus 3 halves x to the negative 1/2 minus 7 halves x to the negative 3 halves. Ugh, all those fractions in the exponents there. Right? Take our function here, the 3 halves is the power, so the power comes out front, and then lower 3 halves by 1. 3 halves minus 1 is 1/2. Okay, 1/2, bring that out front, so minus 3 halves. Lower the power by 1, so 1/2 minus 1 is negative 1/2. And then negative 1/2 times 7 is negative 7/2. Minus 1 gives you negative 3 halves. There's your answer. Okay. Questions on number 2? We'll do one more here. Uno más. F of x equals tangent of x. Now, why did I put tangent of x, which is not a quotient? Right? Tangent of x is just tangent of x. I didn't tell you anything about tangent of x. Why did I put tangent of x in here? Yeah, Cassie.
Because it equals sin x over cosine x.
Yeah, tangent x is sin x over cosine x, which is a quotient. So I didn't show you the derivatives of the other trig functions yesterday because we can actually figure them out. If you know sine and cosine's derivative, all the other trig functions we can evaluate now. All the derivatives of the other trig functions we can find. So for example, tangent of x, we know tangent of x's derivative because we know tangent is sine over cosine. So by taking the derivative here, again it's the bottom, so cosine, times the derivative of the top. So the derivative of sine is cosine, minus the top, so sine, times the derivative of the bottom. What's the derivative of cosine? Negative sine. And again, this is Elizabeth and Nick, you guys missed that yesterday, the derivatives of sine and cosine. So, and then all over the bottom squared. Okay, so let's see here, cosine times cosine, well that's cosine squared, right? Negative sine x, and then a minus sine x, that's going to become plus sine squared of x, right? It's a minus sine x times a negative sine x there, so it becomes plus sine squared x, all over cosine squared of x. Oh my gosh, but what's cosine squared plus sine squared? 1. And what's 1 over cosine squared? Secant squared of x. So the derivative of tangent is secant squared x. Pretty neat. Alright, so there that is. Okay, by a similar method you can find the derivative of cosecant, and I think you should also be able to do secant and, or sorry, cotangent as well. You should be able to cotangent and cosecant and secant now as well. You should be able to figure those out. Should work, yeah, because you know the quotient. Yeah?
Can you, like, explain to me, so f, like the f prime x equals cosine x times cosine. How did you get all that again?
Sure. Yeah, because you weren't here for the stuff that we did. So the derivative of sine of x, which we learned yesterday, is cosine of x. Derivative of sine is cosine, and we didn't like do anything fancy. I just kind of like just told you that. There is a way to prove it. It's kind of, again, beyond what I want to worry about right now in our class, and maybe your calculus teacher, if you guys take it, will show it to you. It uses something called the squeeze theorem, I'm pretty sure. And then the derivative cosine is negative sine of x. So knowing those two things, when we go to do our quotient rule here, okay, and again, you're okay that tangent is sine over cosine, right? So it's the bottom cosine times the derivative of the top. Derivative of sine is cosine, so that's why we get a cosine there. That's the derivative of the sine right there. And that comes from the bottom. So far, so good. And then minus the top, sine, times the derivative of the bottom. Derivative of cosine, negative sine. So we get a negative sign there. So far, so good. All over, and then the bottom, cosine squared. So cosine squared x. Oh, it's frozen. Thank you. So anyway, but you're following it, so you're good though? I mean, you see that?
Yeah.
So now that I'm pointing at things that you can see, okay, cosine times cosine is cosine squared. Negative sine times negative sine, positive sine squared, and then all over cosine squared, which then cosine squared plus sine squared of x, that's that Pythagorean identity that we talked about before. It's 1 over cosine squared, secant squared. Okay? Makes sense? Yeah. So, good. So you guys can figure out the other ones if you want, or not, that's okay too, I understand, but I think it's pretty neat. Okay? So, what I've got for you then, well, on the back of that differentiation product rule paper, you've got some quotient rules to try. Okay? Let's see here. I think if you just want to do like the odds, that'll be good enough, because these take some time. So just like the odds should be fine, okay? Just like the odds. Okay, it's like 1, 3, 5, and 7. Because those take some time and they're a bit of a headache. Okay? So that's all I got for you.